Now we also will study polynomials of degree 2. Speak about some properties of these. Now we have seen the simplest version of these, namely polynomial px equals x squared, or of course what is as simple is just the polynomial minus x squared, so I indicate it in this way. And then we have the following graphs. So y is equal to x squared is this one, and y equal to minus x squared is the one that you get by drawing the mirror image in the x-axis. Minus. We have a minus here. Now let us look at the general version. Bx equals a0 plus a1x plus a2x squared. Now the pictures, the graphs have the same form. So for instance it can be like this. And this is typically the case when a2, constant a2 is positive, like in the case of y equals x squared, where a2 is 1. Or it can be like this. And this is a picture of the case when a2 is smaller than 0. a2 is negative. Now the case that a2 equals 0, of course, implies that we do not have a polynomial of degree 2. Now, you can already easily know some facts about this. Well, the domain, of course, as with all polynomials, is the set of all reals. But what is the image of the domain? It's not the set of all reals. No, it's a subset of the set of all reals. So it's much smaller. And in fact, you can draw it. In this case of the first one over here, you get this set. So I have to put the variables corresponding to the axis. And in the second case, it is something like this set. So it's a much smaller set. Okay, now if we now, by the way, these graphs are called parabolas. And so this is the general name for graphs of polynomials of the degree 2. Now what can we say about invertibility? Well, if we look at the set of all realized values, then if we take one of these realized values, then obviously we cannot deduce the input uniquely from this realized value. And as before, we have to restrict our domain to make this recover process unique. So for instance, we can take this as our input set, so this as our domain D, or as in the second case we could take this as our input set, our domain. And if we restrict our input values, of course, then we can make it such that we can recover the input variable in the uniquely from each realized value. So in the first case here, over here, we can find it in this way. So we have a unique input value x corresponding to this realized value y. And in the second case, well, say we have this realized value y, then we can recover the input value uniquely in this way. Okay, so not invertible. So this function is not invertible if we take the domain equal to the reals, but it can be inverted if we take it if we take the domain equal to some well-chosen subset of the reals. Now, but these questions all involve are centered around the question of how this parabola is located. So this will be the main question. How can we recover from our formula where the location of this parabola is? And to answer this question, I will use a simple example. Say, suppose that we have the following polynomial. We have the polynomial x squared minus x minus 6. So our a0 is minus 6, a1 is minus 1, and a2 is equal to 1. Now, in the first lecture, we had a method of solving a quadratic equation. So the quadratic equation x squared minus x minus 6 equals 0. So what we did was, in fact, solving the roots or the zeros of this polynomial. And what you did was the following. So we looked at this formula and what we wanted is to make a square of this part. And how did we make this square? We just wrote down the formula x minus half of the coefficient of x, which is half of minus 1 is minus 1/2. We square it and then we remove the brackets, and then we get x squared minus half x minus half x, so it's 2 times, so we get minus x, and we get plus the minus half to the power 2. So this is minus half to the power 2 is plus 1/4. And so this part x squared minus x can be written as the square minus 1/4, and we plug it into our polynomial. So what we get in that case is that px equals x minus 1/2 squared minus 1/4 minus this 6 is x minus 1/2 squared minus 6 and 1/4. Now, from this point on, what you can infer already a lot of information, because what we know, of course, is that clearly a square is greater or equal to 0. So these values of this polynomial are always at least minus 6/1/4. Of course, the coefficient of x squared is positive, so we're in this case. And so the minimal value over here is minus 6/1/4. And when is this minimum value attained? So minimum value is minus 6/1/4. This minimum value is attained when this quadratic term is equal to 0, because it can never be smaller. So it is attained for x minus 1/2 equals 0, so x equal to 1/2. Okay, now what is this point? This is exactly this point. This minimum point. So already from rewriting this polynomial in this form as a quadratic term and plus or minus a constant, we know a lot about this parabola. Now the second thing which helps us to determine the location of this parabola is by calculating the roots. So we calculate the roots. As I said before, it's just solving the equation x squared minus x minus 6 equals 0. So we have to calculate x minus 1/2 squared minus 6/1/4 equals 0, and that is easy in this case because we already have written it in the form of a squared plus or minus some constant term, So this equation equals 0 when the square is equal to 6 1/4. And so what we have is that the term that we squared has to be equal to either the square root of 6 1/4 or minus. Now if you calculate it, then 6 1/4 is 25 over 4. So what we have is that x minus 1/2 is equal to the square root of 25 over 4, which is equal to 5 over 2, or it is minus this root, so minus 5 over 2. And then we easily can infer that x either is equal to 5 over 2 plus 1/2. We take this term half to the other side, so we get 1/2 plus 5 halves, so this is 6 halves is 3, or x is equal to minus 5 over 2 plus 1/2, so this is equal to minus 4 over 2 is minus 2. And now it's easy to make the exact location of this parabola precise, so it's difficult to draw it, I guess. So we have to make this picture a little bit smaller. So say we have here the value minus 6 1/4, and we have, well, the proportions are not quite correct, but it doesn't really matter. So we get this minimum point over here, and if we go 5 over 2 to the left, so we get, then we get to the point minus 2. So, well, minus 2, and we get 5 over 2 to the right. Then you have to draw this horizontal axis a little bit bigger. So we get something like here, 3 in green, and we get this parabola. Well, the scales of course are a little bit wrong, but okay, we now can draw it. So this distance and this distance have to be equal. So this is distance of 5 over 2, and this is distance 5 over 2. Okay. Now the picture is horrible, but okay, so this is the way to draw this parabola, and then of course once you know the exact location you can infer something about the set of realized values and ways to recover inputs uniquely if you restrict your input set to a suitable subset of the reals. Now there's one more consequence that I would like to note, because we didn't discuss it earlier, is that we have yet another way of rewriting this formula. So we have this formula which we can rewrite in this way, but since we know that it has 2 roots, we can also write this formula for our parabola, for our polynomial, in the form of x minus root 1, the first root, times x minus the second root. And so what are our roots? So we have x minus, well, root 1 is minus 2, times x minus 3, so it's x plus 2 multiplied by x minus 3. So there's yet a third way of writing the formula of this parabola. Now if we have equal roots, then you can do this whole analysis in a similar way, but then equal roots means simply you can interpret it as having 2 equal roots and then plugging in these formulas as well. Now this third way of rewriting the formula of our polynomial is called factorization, similar to factorization of prime numbers in some sense. Yes, one final remark. I would like to emphasize that this point of the parabola is called the top. We will denote it by top. That's it.